This is the screencast for section 9.1, example 4. Now we're actually going to define what a power series is. Now a power series is an expression of the form, so it's summation, some coefficient that can change each term, times x to a power, and that power is going to change depending on what term it is. So you can see c sub 0, our leading term, plus c sub 1, another coefficient with x to the first, plus another coefficient x squared, plus another coefficient x third, etc. Now that power series is centered at x equals 0. Now what that means is, if I take just one term, it's not going to be a very accurate representation of this whole function. If I take two terms, it's going to be a little bit better. If I take three terms, it's going to be a little bit better. The more terms I take from this infinitely long power series, it's going to better represent the actual function at hand. So that accuracy is going to be centered at x equals 0. So I'm going to start at x equals 0 and get more accurate to the left and right of 0 as I add on more terms. Now a power series can also be centered at a different value. Let's call that a. And then that way, that series will get more accurate to the left and right of a as I add on more terms. Of course, with infinitely many terms, it would be exact. Now, a very basic example of this. If I have a geometric series, the sum from n equals 0 to infinity of x to the n, well, that's going to be x to the 0 is 1, plus x to the first, plus x squared, x cubed, etc. And that represents 1 over 1 minus x. That is a geometric series. So we have 1 over, that was the leading term, 1 over, 1 minus, and then the r value is actually x in this case. So 1 over 1 minus x. Well, this function, 1 over 1 minus x, is down here in orange. Now, I'm centered here at x equals 0. If I just have x equals 1, or excuse me, y equals 1, that's this line right here. Not a very good accurate representation of the orange curve. But now what if I add on another term, 1 plus x? Now the one with two dashes there, that represents two terms. So that goes here. A little bit better, it starts to curve along with it. Now, how about three terms? Well, that's this one, getting a little bit better. 4 terms, well, let's see, 4 is over here actually. 4 terms, this one, it's going to get a little bit better. 5 terms, 6 terms, 7 terms. Eventually, the more and more terms I add on, you can see it's starting to get more accurate as we go away from x equals 0. Now, if this were centered around x equals, let's say, 0.5, then we'd be getting more accurate to the left and right of 0.5 as we add on more and more terms of this series. Now, we can take a power series and differentiate it, and we get a couple conclusions from that. If the original series converged, its derivative will converge on that same interval. Now, we also can make another conclusion, which well, it really implies that if the derivative of a function equals another function, then the derivative of that original function's power series is going to equal the power series for the other function. And that's what example 4 shows us. So example 4, we're going to find a power series by differentiation. So we're given that 1 over 1 minus x, which maybe looks familiar to you, is represented by that power series. That's what we just discussed on the previous page. On the interval -1 to 1. We're going to find a power series to represent 1 over 1 minus x squared. Okay, so first let's take a look at the relationship between 1 over 1 minus x and 1 over 1 minus x squared. So I'm going to take the derivative of 1 over 1 minus x, which is the derivative of 1 minus x to the -1, and I do in fact get 1 over 1 minus x squared. So, since the derivative of the original function is the function I'm trying to find the power series for, I can say that the derivative of the power series for 1 over 1 minus x is going to equal the power series of 1 over 1 minus x squared. So if the derivative of f equals g, the derivative of f's power series equals the power series of g. Alright, well let's take that then. that means the derivative of 1 over 1 minus x is going to equal the derivative of its power series. And that's what I'm trying to find G's power series. So the derivative of 1 over 1 minus x is 1 over 1 minus x squared, which means to get its power series, the derivative of 1 is 0, derivative of x is 1, the derivative of x squared is 2x. Keep going, the derivative of x cubed is 3x squared. Then we have this pattern, so now we're not using x to the n anymore, we're using the derivative of that. N times, so the exponent becomes a coefficient, x to the n minus 1. Now the exponent is 1 less. Now again, that's going to be on the same interval, -1 to 1. And I know that doesn't really sound too concrete right now. It hasn't been proven. It just seems a little bit logical. But trust me, for now, we will prove it later. Now what I want to show you is how this representation works. On wolframalpha.com, I searched for the power series for 1 over 1 minus x squared, just because that was my ultimate goal in this equation. It gave me this series expansion, which turns out to be what I have, 1 plus 2x plus 3x squared plus 4x, etc. And then here's the graph it gave me. The first term, y equals 1. Then two terms would be y equals 2x. Then we've got this one, plus 3x squared. So right now it's just y equals 1. Then it would be 1 plus 2x. Then it would be 1 plus 2x plus 3x squared. Then we'd go even further, 1 plus 2x plus 3x squared plus 4x cubed. And we would keep getting more and more and more accurate as we add on newer and newer terms. And as you can see here, the curves are getting closer and closer and closer to the original as we add on more terms, but between -1 and 1. And I know you'd need more terms added on to see that, but that's what this means, is that it converges on the interval -1 to 1. So the power series for 1 over x squared will be a good approximation only between -1 and 1 on the interval of convergence. Now because this is a geometric series, if the absolute value of x is less than 1, so if I take any of those values between -1 and 1, the series will converge for those values. In other words, if I plug in 0.5, the series will converge. If I plug in 0.7, the series will converge. If I plug in 1.2, the series will not converge. Now try problem number 27. Says use the series and the function f of x that it represents from the indicated exercise to find a power series for f prime. So we're not comparing two series in this case, we're simply finding the derivative of this power series. So I'm going to expand the power series first. Let's see, if n was 0, my first term would be 1. If n was 1, it'd be 2 to the first x to the first, plus 2 squared x squared, 2 cubed x cubed, plus, you get the idea. That is a geometric series. The first term is 1, and the r value is 2x, actually. Each one gets a new 2 and a new x. So that's going to have the formula 1 over 1 minus 2x, which is a little bit different than 1 over 1 minus x. Keep in mind what kind of change happened there. So let's find the derivative. The derivative of that 1 over 1 minus 2x is going to equal the derivative of the power series of 1 over 1 minus 2x. Alright, so the derivative of 1 over 1 minus 2x is this mess right there, which we'll simplify in a minute. Now the derivative of each term here, we get 0 plus 2 plus 8x plus 24x squared plus, okay, so to figure out this series, what the derivative is going to be, it's a little weird because it's 2 to the n, x to the n. I mean, there's going to be n in the front, x to the n plus 1, but what happens to that 2? Well, alright, if I look here, I have 0. Here I just have 2 times 1 maybe. Here is 2 times 2 times 2. Here is 2 times 2 times 2, so 8 times 3. The next one I'm predicting will be 2 times 2 times 2 times 2 times 4. So I can kind of see the pattern of the 2's. The 2's, we have, first of all, n, which we said the old exponent becomes a coefficient, n, 2 to the n. So we have 0 2's here, 1 2, 2 2's, oh there's actually 3, hang on, 3 2's, 4 2's. So we do have 2 to the n, but that extra 1, 2, 3, 4 comes from the n. So we have 1 2 times 1, 2 2's times 2, 3 2's times 3, 4 2's times 4, etc. So there's your n, 2 to the n, and then we have the x to the n minus 1. So x to the negative 1, 0 divided by x is 0. X to the 1 minus 1, that's x to the 0. X to the 2 minus 1, that's x to the first. 3 minus 1, 4 minus 1, etc. So simplifying the left side here, I have 2 over 1 minus 2x squared, and that's going to equal my first term, 2 plus 8x plus 24x squared, and then my notation here for the expanded series, which in summation notation here would be n equals 1 to infinity of our expression. And that's not going to be on the interval negative 1 to 1 anymore. Remember I said keep in mind what change took place here? If it was 1 over 1 minus x, it would be from negative 1 to 1. But now this is only going to converge. That was a horizontal shrink by 1/2. So it's only going to converge on the interval negative 1/2 to 1/2. Which means the power series for 2 over 1 minus 2x quantities squared will only be a good approximation between the x values negative 1/2 and 1/2. Outside of that, it does not converge. Now I don't have a picture to go along with this one, but I could tell you that if I just graphed 2, it would be a very inaccurate representation of this function. 2 plus 8x would get a little bit better. 2 plus 8x plus 24x squared would get even better. 2 plus 8x plus 24x plus 64x cubed plus, keep going on forever and ever and ever, would get more accurate of a representation of this function between the x values negative 1/2 and 1/2.